Good morning, Fancy Meat Computers! How's everybody doing today? Let me just check the sound. Wonderful. We're trying something new today. We're trying the low latency stream today. I had to retrieve myself a cup of tea, which is actually water. It's like in the movies where they say they're drinking like beer, but it's actually water that's had food coloring put in it. Everybody wants to sleep? Yeah, I hear you. I hear you. Don't worry. We're like today's Wednesday. It's like halfway through the week, so soon you shall have your break. And then it's right back to the grind. 1080p when? When YouTube gets its act together, that's when. Hoyo! Yeah, I don't think I can, actually. I don't think I've got a setting for that. Let me see. Stream settings. Bloop-a-bloop. Latency. Doop-a-doop-a-doop. Nope. They don't really let you set that. Well, maybe, like, maybe in OBS I've got settings for that. Maybe I'm intentionally streaming at 720. Output. Video rate. Audio bit rate. Video. Okay. So my output scaled resolution is currently at 1280 by 720, which I'm not sure if that's 1080p or not. My base canvas resolution is 16 by 900. I don't know. No, it's like I believe it's in OBS. That's 720? Oh, okay. See. Oh, so it's doing it by the height then. Yeah, that would make a certain amount of sense. So I experimented with it, you know, earlier in my existence, and I, you know, that this worked reasonably well. Like if I start pumping out too much, you know, it would screw up on me. But at the same time, that was before I had my internet fixed. So maybe I could manage a 1080p stream. I'll tell you what. We got a motor on this material, so somebody shoot me an email and remind me. I'll see if I'll play around with it, see if I can get a 1080p stream going for you guys. You know, since that would also address some of the issues with respect to the print being a little bit small to see, because it's terrible for it to be small to see and be kind of pixelated. So Windows 11 isn't even all that, to be honest, lol. Windows isn't even all that, to be honest, lol. Never mind Windows 11. It's like, I'm sad now because there are more what is it? There are as many versions of Windows as there are Mega Man games? Or is it, I don't think they've done Mega Man 12 yet. Alright, let's go. So last time we were talking about lists, and we were talking about the standard operations. We were sort of playing around with lists, you know, poking around in the corners of it, you know, seeing how things behave in certain edge cases, which is very useful and interesting information. Let's talk about aliasing now. So this is gonna probably bake your noodles a little bit. So things don't always work the way they seem. And I'm about to show you some of the old magics. That's right, folks, we are about to delve into the elder magics. I'm about to show you how Python does some of the things it does under the hood. There we go. It's as close as I can get it. No. Increase size. There we go. Thank you. So here's the thing, right? Let's say we had a list, right? 1, 2, 3. Let's say we wanted to assign this list to another variable. So let's say lm, m is equal to L. All right? So L is this, m is also that. Let's say we perform an operation on L, like L at 1 is equal to whatever. Oh yeah, magic is totally real. 1, whatever, 2. There you go. But if I take a look at M, you'll see that the modification that I made to the L array also shows up in the M array. So so what the heck is going on here? Well, it has to do with what's actually going on with L and M here. So the way that your computer represents M and L is as an address. It's a pointer. This is how we'll talk about it in 1xc3 next semester if you decide to take it. But yeah, it contains a value, but that value is a memory address. So it's pointing to some area of the memory, right? So when I assign the value of L to M, what I'm actually doing is I'm duplicating a reference to data rather than duplicating the data. Incidentally, if you do this with tuples, it doesn't work. I believe it doesn't work. We'll see. T and U is equal to T, T, U. Well, you can't modify tuples after you create them, so that's a good reason why that doesn't work. Yeah, so this is, yeah, pass by reference. That's kind of, yeah. How to exchange multiple elements in a list to string. You just use string, and then you put the list inside the string, and that turns it into a string. Oh, it doesn't work. Never mind. You know what? That's different. Not going to answer that question. Figure it out. Use the documentation. Bah. So, mutability may lead to aliasing, which is a source of errors. So this is not what you would expect to happen, right? Because it's not what you expect to happen, it can result in errors. So if, for example, I'll show you how to break this real quick. If you let's create N, for example, assign L, and use the slicing operator. So N is the same thing as L. If I modify L, 12, sure. L is 12 whatever 3. M is also 12 whatever 3. N is still 1 whatever 3. So because the slicing operation is a non-mutating operator, the reference is broken, right? So this slicing operator produces a new version of the list, which is being stored in N. It's not referencing the old version. So N, when you modify L after the creation of N is not modified by that. But as you can see, M is. So what's going on here actually? Let me just hex. So you can get the actual, what's called the memory address of a list, or any data structure really, by using the ID function. The ID function in combination with the hexadecimal function converts it to hexadecimal, which just makes it easier to read. So if you take a look, the ID of L is this long number, which is in hexadecimal. We're going to talk about hexadecimal, but not now. It's just another way of representing numbers. And M, you'll see, has the same address. N, however, does not. It has a different address, and that's the thing. Because L and M have the same address, they are the same thing, right? They point to the same data. The data, you have to abstract in your brains, pull the data away from the variables. The variables are references to the data. The data exists separately off in your memory. Cool. All right. What if I did L and M tuple L? Ah, yeah, so if you if you do a tuple conversion, you'll see you get a different address again. So that means that it's a tuple. If you take this and cast it as a tuple, you'll create new memory as well. So, what is the definition of aliasing? I understand your demonstration, but I don't know how to rephrase it in words. So, aliasing is the stupid Python term for exactly this property of multiple variables pointing to the same data. It's like you have two aliases for the same data. An alias being alias define an assumed name, an alternate name or address, especially an email address that forwards all incoming email to another address. So that's kind of the idea of what an alias is. What if you manually modify the bits of the address of a tuple? Is that a thing you can do? Not really in Python. Not really in Python. That's definitely a thing you can do in C. That's called pointer arithmetic in C. And I think, hopefully, just hold on to that line of curiosity until we hit 1xC3, and then we'll fully explore it. So, aliasing. Another interesting thing you can do with aliases is you can actually include lists inside of other lists this way. So if we had Q is equal to 1L3, then you can see that when you print out Q, you get the value of L, so to speak, printed out with it, even though inside of this is still an alias, right? So if I were to modify M, M at 1 is equal to bark, then Q, that change is still represented. Can you manually alias things as well? For example, define integer variables and have same pointers like in C++. So Python typically doesn't like you playing with these things. I'm sure there's a way to do it, but it's beyond the scope of this class. Yeah. This is trippy and a recipe for bugs. Thank you for noticing. So here's another little complication that here's another little monkey wrench I'll throw in the gearworks for you. When you pass something like a list into a function as an argument, Python functions do pass by assignment. Assignment, in the case of lists, means creating an alias. So, while modifications to a regular variable used as a function argument do not pass outside of a function, modifications to a list, which is provided as an argument to a function, will pass outside of that function because you're dealing with an alias. So there you go. Yeah, it's a two-way alias. If you change either one, the other one changes too. Yes! Yes. So, you guys... yeah, we pass by assignment as well, says a student. Yes. You also pass by test and pass by exam. So yes. This is a fairly long, complicated derivation. What is the value of E at the end of this? At the end of this long derivation, right? So, A is 1, 2, 3. B is equal to A. You know what? I might actually just do this. You guys can, or maybe I'll do a poll. A, B, C, D. Man, I wish that I wish this thing had, what, like one more slot, eh? So. So, A is 1, 2, 3. B is equal to A. C is equal to 4, 5, B. A at 0 is equal to C at 1. D is equal to C at 2. E is equal to D at 0. What is the value of... So we've got most people voting for E here. Let's take a look. What is the value of E? So you guys are saying it's either 5 or 4. It's 5. Ta-da! Oh, a lot of votes were just coming in. It's 5, right? Because D at 0. Like, so A, we've got that. B is the same as A. C is 4, 5, 5, 2, 3. D is 5, 2, 3. So again, D is C2. C2 is this guy, so D is also an alias of A. And so, of course, the first element of any alias of A is going to be 5. Ta-da! So there you go. Slicing. So we've talked about slicing a number of times. We'll just review it quickly. Slicing and many other operators work uniformly on all sequence data types. So things like strings, tuples, and lists. Doesn't work on dictionaries or sets because those are not ordered. They're not ordered data types. And we'll see what the difference is. I put a 1 on the slide for A at 0. Where? Huh? I don't see it. So basically, the slicing operation, once again, let's create a string. This will be easiest. There we go. So, S. So you have it from I to J to K, right? So the first colon you can say to, and the second colon you can say by. So we could say 1, 2, 7 by 3. 1, 2, 7 by 3. And that gives you what you need. If you leave the first element out, where that starts us counting at the beginning of the data structure. If you leave the second element out, that takes you to the end of the data structure. And of course, you can always leave the third one out. That just means count by 1. So, there we go. So if you want to duplicate something, create a new memory address for it, you can leave the first one blank and the second one blank, and that just duplicates the entire list in a new memory. Dictionaries are ordered in Python 3.6 plus. I thought they just had a special ordered dictionary. Like regular dictionaries aren't ordered, but they do have an ordered dictionary type. I thought that was the distinction, but perhaps I'm wrong. I might be working with an older version of Python in my brain, which is entirely probable. Thank you. So, another neat little trick is that you can count backwards by using -1 here. So, it doesn't work when your lower indice is lower than your high indice, but hopefully it works in reverse. So start at 15, stop at 3, count by -1. There you go. If you leave both of these blank, this is like quick Python for reversing a data structure with a slicing operation, which is kind of cool. Reverse operations that are so compact are occasionally useful. So, there we go. I'm going to skip the rapid fire round because it'll take too much time. We got to keep moving. So, lists versus tuples. Tuples are like lists, but immutable. So, there's no aliasing on tuples, and tuples are faster. Obviously, all of the interesting things that happened with aliasing, you need assignment for those to work, and since you can't assign the elements of a tuple, that just completely destroys any idea that you might have had that you could alias tuples. So there you go. We already know what a tuple is. So, let's move on and talk about sets. Sets as in mathematical sets, as in set theory, as in naive set theory, which you may wish to study at some point. Probably your first year discrete math class is going to be primarily concerned with teaching you set theory. We don't have to know all of the elements of set theory right now. Basically, your high school understanding of set theory will be sufficient for the time being. So, sets in mathematics are unordered collections of objects without repetition. For example, the set of all even numbers less than 10 is 0, 2, 4, 6, 8, or equivalently 4, 2, 6, 6, 8, 8, 0, 4. So the idea is, in a set, there's no repetition, right? If you were to take 4, 2, 6, 6, 8, 8, 0, 4 and convert that to a set, you would get 0, 2, 4, 6, 8, except that the elements wouldn't be in any particular order. So you cannot assume ordering over a set, even though sometimes it looks like you can. Your operations in mathematics on sets are as follows. Number 1, union. A new set containing all of the elements in A and all of the elements in B. Actually, I should probably pull the class. Do you know anything at all? Or, no. Did you do set theory before? Have you done? My God. Have you done set theory before? It's not difficult to understand the basics of set theory. Set theory is very interesting because it's one of these fundamental mathematics from which, like, all other branches of mathematics can eventually be derived. So it's, you know, if you're interested in math and stuff, it's a good thing to know. Oh my goodness. Okay, so. So in data management, you might have seen set theory. So about a third of the class knows what the heck I'm talking about. So I think we'll take just a very brief moment and talk about sets. So, let's see here. So, the best way to describe it, I think, is Venn diagrams. Set operation Venn diagram. This guy will do. Right. So sets are very much... so what is a set? A set is just a collection of objects, right? You can have a set of numbers. You can have a set of jelly beans. You can have a set of tests to write. You can have a set of leaves on a tree, right? So long as all of the elements of the set are unique, it is a mathematical set. Very often you'll have heard of the natural numbers, right? That the natural numbers start at 0 and count up by 1 all the way through to infinity. That is a set, right? The integers are also a set. That's a set that includes all of the natural numbers and all of the negative ones too. So we say that the integers are a superset of the natural numbers, or that the natural numbers are a subset of the integers, right? Because, like, basically just take all of the numbers that are the natural numbers, throw them all into a bag, shake the bag, and that's a set. So, you have operations. I thought 0 was not a natural number. You'd be wrong. 0 is very much a natural number. Very much so. At least it is in my third year class. I don't know about the classes you take. It's kind of like, it doesn't really matter what I say. If your professor for your course says something different than what I've said, then you have to listen to that professor. But yeah. So, set operations. So if you imagine like two sets, set A and set B, you know, you could even do like, you know, my favorite songs, your favorite songs. That would be an okay way to think about this as well. So I have a set of favorite songs, you have a set of favorite songs, right? So you can perform set operations to get different sets from those sets. These work very similarly to the Booleans. So the easiest one to know is union. So the union of two sets is the set of all objects which are contained in either set, right? So it's all of the songs I like plus all of the songs you like collected into another set, right? Of course, if we like some of the same songs, then we don't count them twice, right? We only count them once. Intersection is this guy up here. This is intersection. Intersection would be just the songs that both of us like, right? So it's the set A intersected with the set B. That becomes only the song that, if we're dealing with the songs we like, that's just the songs that both of us like. Now, it's also possible that the sets might not intersect. If the sets don't intersect, then the intersection of those two sets is what we call the empty set. So you can have a set that contains nothing, right? So if, like, I'm really into, like, classic, if I'm really into, like, classic rock from the 70s, and, like, you just don't have anything on your list of favorite songs that isn't, like, electronic dance music, then, you know, there's gonna be no intersection there, which means that the set of songs that we both like is empty. So that's what an empty set would be. If you put a bar over top of something, that inverts it. So the inversion of the intersection is all of those elements that are exclusive to either one, but that's not really important. Don't worry about this one because we're not going to talk about it in the slides. A set minus B. You have to say set minus here. You sometimes see this as a backslash as well. So set A minus set B would be all of the songs I like so long as you don't like them. Right? But yeah. So those are your elementary set operations. So that's union, intersect, difference. Oh, and cardinality is easy. That's just the number of elements in the set. Cardinality is just the size. I have some questions. I think traditionally natural numbers are 1 to infinity and whole numbers are 0 to infinity. Apparently there are different definitions for the natural numbers. Some include 0 and some don't. The ISO or IEC 80,000 considers 0 a natural number, so most sources consider 0 a natural number as well. If 0 is a natural number, what's the point of the whole numbers set? You don't need one let me, so what's the name of the last type of subset? This guy, did I close that? Did I do something stupid? I think I closed it and did something stupid. The last one that I talked about was set difference. Set minus, set difference. You know, minus is like the minus sign, but, you know, sometimes it's a slash. But yeah. So let me tell y'all what things are like around these parts. Whole numbers doesn't get its own set unless you decide to define whole numbers as a set. You would say it is the natural numbers set minus the set that contains 0. Whole numbers are defined in terms of the natural numbers. Integer. So you've got 3 primary sets of numbers. You've got the natural numbers, the integers, and the real numbers. Natural numbers correspond to unsigned integers in computing. Integers correspond to signed or normal regular integers in computing. And the real numbers correspond to float or double precision floating point numbers. That's what double means. It's double precision floating point number. What? Yeah. Is the cardinality of A just a number of elements in A, since all elements in the set are distinct? Yes. Yes, it is. So, here are your set operations. So, to create a set, you use curly braces. So, the set 1, 2, 3, 4, 5 is a set. S is equal to 1, 2, 3, 4, 5. If I include duplicate elements in that, you'll notice that the duplicate elements are removed. You'll also notice that these elements don't end up in the order you put them in, right? Notice we entered 21 over here, but it ended up there. But this is also not ordered, right? Because 23 appears after the 54. So this is a tripping hazard with this material. Sets might look semi-ordered, but they're not ordered. You can't rely on the elements of a set being in any particular order. So indexing operations do not work over sets. So you can't just like pick out the 4th element, because it's like the concept of 4th makes no sense in this context. Question: can empty set also be the empty curly braces? No, because that's been reserved for empty dictionaries, which are much more commonly used. So they get priority, and they get syntactic priority. Yeah, so if you want to create an empty set, you say, you know, S2 or S1 is equal to set with nothing in there. So S1 is an empty set. If I S1 union and set containing 1, you can see S1 is still the empty set, because I think these things are immutable. There you go. So you can perform a union operation to add things to a set. So if I have 2 sets, say I have 1, 2, 3, 4, and set 2 is equal to 2, 4, 3, 4, 5, or yeah, that'll work. S union T is 1, 2, 3, 4, 5. S intersect T is 2, 3, 4. S minus T is just 1. T minus S is just 5. The length of S is 4, and you can test for membership in a set using in. So is 3 in S true? is 6 in S, false. There we go. So why does it swap around 21, 54, and 23 like that? It just does. It's because sets are not ordered. The ordering doesn't matter. It's like, I don't know how it decided to, why it decided to put things in the order that it decided to put them in. I don't know. I don't know what's going on behind the scenes there. All I know is that you can't rely on these things being in a particular order. Although this is the order in which things will be popped out of the set. You can't rely on ordering with sets. Sets are unordered collections. That's the primary and most important property of sets as compared to all the rest of the things. So are sets immutable? Well, let's see. We've got S. Let's create U, assign S to U, right? S equals S intersect 6, or union 6, sorry. So that's that. Is U the same? It is not. So sets are immutable. Ta-da! Although they might have some mutating operators. Yes. So set operations that modify the set. So we do have a set of mutating operators, but the whole assignment thing doesn't work with sets. Because, again, there's no index to be able to access things with. So if we wish to add an element to a set, s.add 3. There you go. S.remove removes an element from a set. So you have to know that it's in there first before you can remove it. Return and remove an arbitrary element. So s.pop will take something out of the set and return it to you. As I said, it's picking things out in the order that they appear when you print it, but the order that appears when you print it is arbitrary, so it doesn't really matter. It's still an arbitrary decision. It's like computers can't be truly random, but they can be deterministic but arbitrary. It's like it makes strange decisions that it doesn't tell you about. They are like repeatable, but you don't know the mechanism, so for you it's as good as random. Is a set like a stack? A stack is ordered, so no. A set is like an unordered stack. How is it immutable if you can change the state of the set? Well, it's probably mutable, but funny about assignments. Yeah. Actually, never mind. The order doesn't say the same. The set is hashed, so set operations are efficient. Yep, probably. Yep. But again, that's kind of under the surface details that we're well beyond the scope of this course. So, counting elements in a collection. So, you can use sets. This is one way that you can sort of practically use sets. To count the unique elements in a set, one way that you can do it is you can declare an empty set for each element in a list or some other data type. S is equal to S unioned with that element, and then you return the length of that. And that's, that's one way to do it, but there's also a faster way to do it. Set convert. And take the length. (21). That's the number of unique elements. You don't need these. You don't need a function for it. You can do it in one line. Is discard the same as s.remove? Yeah. Oh, did I use remove accidentally? I did use remove. Yeah, s.discard. Let's see here. What do I have a set? There we go. T.discard. discard 3. Yeah, remove and discard do the same thing, as far as I can tell. Good. So, again, we'll skip the rapid fire round because this is not an in-person class. So far, tuples, round braces, duplicates are allowed, order matters, and immutable. Lists, square braces, duplicates allowed, order matters, immutable. Sets, curly braces, no duplicates, order doesn't matter, but it's mutable. It's got mutating operations, so it's mutable. But, again, assignment is kind of funny with it. But maybe, maybe if I use the mutating operators, it'll work. So S is equal to T. T dot add Q. T has Q in it. S also has Q in it. Oh, okay. So if you use... the problem I was having was that these set operations are non-mutating operations in the same way that list slicing is a non-mutating operation. So that's why it was messing it up for me. That's why I thought it was behaving like an immutable thing when it's actually mutable. All right. So, good. Excellent. Let's talk about dictionaries. Dictionaries are actually fairly similar to sets. The big difference between a dictionary and a set is that with a dictionary, we do allow indexing. We're allowed to do indexing over a dictionary, but we have to define what it's indexed over. So, if we have a dictionary D, and we create a mapping from 1 to apple, from 2 to orange, and from 3 to Omastar, the Pokemon. D at 1 is apple, D at 2 is orange, and D at 3 is Omastar. However, you may say to yourself, this looks suspiciously like a list. What gives? This doesn't seem useful at all. And, oh my friends, watch this, because we can totally do that in reverse. So, Kabuto leads us to fruit. Diglett leads us to candy. And Zapdos leads us to the worst. So, D2 of Kabuto leads us to fruit. So this is the thing about a dictionary, is you can look things up by things other than numbers. Yes, I'm a Gen 1er, so yes, Gen 1 of Pokemon, it's the best. They've never surpassed it. Do sets act like tuples when it comes to memory management? No, they perform more like lists when it comes to memory management, because they're also mutable. Yes. Okay, so dictionaries are kind of fun. You can add elements to a dictionary fairly easily by just assigning to an element. So if we wanted to say Snorlax is equal to the best, for example, and we ask to view the dictionary, you can see that Snorlax the best has been added to the dictionary. Dictionaries are actually an extremely useful data structure. So, can you mix types with elements and indexes? Yes, so I'm pretty sure that you could do like a 1 now is equal to best gen You can, and then you can access, so you can mix these guys, yeah. D1 is the best. 1 is the best gen. 5 is equal to not the worst gen, but not the best. D5. D2 of 5.2 is best games other than red, blue. There we go. So you can see that you can just kind of create an arbitrary mapping between one thing and another. And, you know, for those of you who are big math buffs and want to know what's actually going on in the in the mathematics here, what we're actually doing is we are creating two sets, and we are creating a relation between those sets. Now, this is the type of thing that you this is something that you'll study reasonably heavily when you take discrete math, which I know all of you are going to take discrete math, right? But essentially, so we have one set, right? We have another set, and we have a correspondence between the elements of these sets. The way that you define a relation in set theory is you have a collection of pairs, right? You have something from A, something from B, something from A, something from B, and you can follow from A to B and vice versa if you want to, using the relation. So that's what a dictionary is. It's a relation in a strict mathematical sense. But for you guys, it's sufficient to know what a dictionary is. Like using it like dictionary, like the terminology that's used in Python is like you have keys and you look up values. So it's like a dictionary in that sense that you have a word and that looks up a definition. So this is like a generalization of that idea. You have a key that looks up a value. So you can actually extract the keys and the values here. So d2.values, that's just the values. d2.keys, that's just the keys. I can see the question bubbling up in the chat. Dictionaries are mutable. They are definitely mutable. 100% mutable. Alright, I think I'm going to call it there, since we're out of time anyway. Any questions? Do computer science students take a lot of maths in the upper years? I would say the number of pure math courses is probably comparable to what you'd see in an engineering program. I'd say there's a good mix between like math type, like mathy courses and like practical, like sort of programming skills with a Z courses. But you know, that being said, it really strongly depends on what professor is teaching what course at what time. You know, like with 3MI3, which I'm teaching this semester, I made a somewhat controversial decision to sort of angle it away from the programming skills type material and angle it more into the math. But yeah. So let's see. Questions. How to populate a dictionary from a sentence? Haha. A split. You want to? I'll show you a fun trick real quick. Pokemon is a fun game. Split on spaces. That'll get you started, I think. Speed running yellow in 7 seconds. Yep. best things about dictionaries is instant search. Yeah. What starter did I pick? Well, I had Pokemon Red version. My brother had Pokemon Blue version. And just because I was boring, I picked the one that was on the box. Like, when you start up Pokemon Red, it shows you a picture of Charmander. So I picked Charmander because I'm a boring person. But also I thought that Charizard was cool. Which he is. But, yeah. But I was also, like, 6 at the time, so, you know. But yeah, my first starter was Charmander. Are both the keys and the elements mutable in dictionaries? Should be, yeah. I think so. Prof, according to you, which year is the hardest for comp sci students? I don't know enough about the program to be able to tell you that, to be honest. I'm from the engineering. I did my bachelor's degree in mechatronics engineering, to be honest with you. So I didn't actually do the comp sci program, so I can't tell you which year is hardest. I know that the third years seem to be having a bit of a rough time at the moment, but that's primarily because I'm teaching them. I think everybody's just having a rough time at the moment. When will using sets be more useful than lists? Rarely. Dictionaries definitely are practical. Sets are really like academic knowledge. Please tell me you don't need to take a linear algebra after the first year. You don't need to. I don't think you need to take an explicit course on linear algebra after first year, but everything you do in computer science is like just a hair's breadth away from becoming linear algebra. So linear algebra is one of those areas of mathematics which is actually extremely applicable to computer science. So I would recommend not hating. I would recommend either not hating linear algebra or developing Stockholm Syndrome with respect to linear algebra, because you're going to need it. I'm not... Maybe once I have my doctorate, then you guys can call me Professor Oak. Yeah, if you're going to do AI, then you deal with a lot of linear algebra. Yep. Have I ever done a Nuzlocke run in Pokemon? No. No. I have not. That would be fun, though. I don't know. I don't have a lot of time for video games these days. Can you have the same two definitions in a dictionary? No. Nope. You're only allowed... So, the keys of a dictionary must be unique. The values can be duplicates. So in that sense, the values are not actually they're not actually a set because you allow duplicates, but you're not allowed duplicate keys. So, like, how would you even add, like, a second Kabuto? Right? Because by referencing Kabuto, you're picking up the first Kabuto. So, yeah, online lectures are just a rough time. Hopefully things get back to normal next semester. Too many firefighting types. Yes. Snivy is the worst. I chose the grass starter in X and Y, and I was like, you're so useless. Why did I even pick you? It's like a high defense Pokemon with no hit points to back it up. It doesn't make any sense. If you're gonna do a high defense Pokemon, you have to give them hit points too. You have to. Ugh. Do you know how a math minor can help with CS? I'm thinking of minoring in math, but I'm not sure how helpful it would be. Well, I think it's either at U of T or it's either at U of T or Waterloo. The computer science degree is, technically speaking, a degree in applied mathematics. Chespin, that's it. He's very cute, but he's useless. Yeah, Chespin is like by the end, I was like, am I really gonna like drop my starter by the 6th gym? Is that where I am now with Pokemon games? My god. My favorite pastime is using close combat on a level 100 Blissey in Gen 4 games. Oh, that's your afternoon gone then. You know, watching that health bar tick down, eh? Uh, yeah. I would say it really depends on the math, but like, there's not a huge um, there's not a huge degree of utility, I would say, at least at this level, in like your sort of integral or differential calculus, that type of continuous math. So if you can find math department courses on discrete math, like math that's applicable, that would be good. But yeah. Favorite Pokemon: Mega Aggron. Or just regular Aggron. I know he's like ×4 weak to like 2 different friggin' types that are very common, but man, I just love my Aggron. When you get him in a good matchup, there's no competition. But again, that's true of a lot of Pokemon. But my cousin scammed me when I was younger and traded my starter for a Psyduck. Oof. Yeah, I did that to my brother once. It used to be in Gen 1, it displayed the name of the Pokemon and not the nickname. So you could trade you could trade someone a Pokemon with a nickname that you had set that they couldn't change, because you can only change nicknames if you are the original person who caught the Pokemon. And so he had blue and I had red, so I traded him an Oddish that I had named Bum, and he was so mad. He's not forgiven me to this day. I changed it back, of course, but can you make multiple save files on Pokemon? No. Nope. It's always only one save file per game. That's how they get ya. There's no reason for that, but that's how they get ya. Toxic running Snorlax with rest and sleep talk. Ho ho. So linear algebra and discrete math is greater than calculus for CS. I would say so. Like linear and differential and integral calculus is still very useful to know, but it's far more highly applicable if you were going into something like physics than if you're going into computer science. Computer science, everything is discrete. Even the things that pretend not to be discrete are discrete. So there has been movement into computer science of the continuous mathematics, but it's always ever like you're spoofing continuous mathematics with something that's actually discrete under the hood. So it's like but yeah, like knowing math is always going to be useful, but I think that knowing discrete math is going to be particularly useful. But yeah. Yeah. It's Oddish in the original ones. Oddish was version exclusive. Yeah, so I had the I was the Oddish master. I was also the Ekans master, and the what was the other one? Growlithe. Growlithe was version exclusive. Caterpie and Weedle were not quite version exclusive, but just like super rare. Like in red, Caterpie was very rare, and in blue, Weedle was very rare, but you could catch them. Do I play Pokemon Go? At one point I did, but since I've been stuck in my house all the time, it's like, when am I ever walking anywhere? My legs have. I know it's like out of the camera view, but like at this point my legs have like atrophied to like blackened stumps from lack of use. Yeah. Anyway, I think I'll let you guys go now. Take care. Have fun. What team was I on? Team Mystic. Like a normie.